Alright, ladies and gentlemen, let's continue talking about section 8.2 and solids of revolution. We already talked a bit about solids of revolution. We used integrals to accumulate circles, areas of circles, which were cross sections of these strange shapes that you can get by rotating areas around the x-axis. So we're going to continue this and use integration to find the volumes of stranger and stranger shapes. Here's the first problem we're going to take on. I guess I'll read it out loud for you. Find the volume of a solid of revolution obtained by rotating the first quadrant region R, bounded by the curve y equals x squared and the lines x equals 1 and x equals 2, about the line y equals negative 1. Let's try to make sense of what the heck this is looking for. Okay, so we're looking for a first quadrant region R. First quadrant means the area enclosed by the x and y axis up here. This is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4. So first quadrant just means that we're looking at the part of a graph where both x and y are positive. So we have some shape that's going to be bounded by the x-axis, it looks like. Let's see here. Here's x equals 1, 2, 3, 4. So we're looking for a shape that's between these two vertical lines. This is x equals 1. This is x equals 2. And it's also contained by the curve y equals x squared. Well, that is a parabola. And it looks roughly like this. Y equals x squared. So the shape in question here that we're rotating is this shape. We'll fill it in. This shape is called region R, and this is what we're going to rotate. Now, unlike the last problem, in the last video, we are not going to rotate this around the x-axis. Instead, we're going to rotate this around the line y equals negative 1. So there's a gap. There's a gap between the shape that we're rotating and the axis of rotation is what we'll call it. So this shape is going to be kind of hollow. It's going to have a hole going right through it. It's going to be kind of donut-ish. And we can still find the volume of this shape. We can watch an animation here to try to get a visual of what this shape is going to look like. Let's just jump right to it here. This top red line here is x squared. This is the x-axis right here. So let's just take a look at what happens. And boom. So here we go. That purple line is the line y equals negative 1. As you can see, we're going to get this shape. It's rotating around. And this is the way this website works. It doesn't give you a solid shape. But you can kind of imagine what this would look like if it was filled in. We'd have this hole right in the middle. And everything between the orange and the blue, you think of it as a solid mass here, something that has some volume. And we can find the volume of this using integration. So let's think about how this is going to work. Here's one of the views of this shape. We're kind of looking inside of it, and we can kind of look through this orange cylinder in the middle. This is going to be a hollow area, and the outside, the blue, is kind of the shell of this shape, and everything in between is the volume. Well, think about it this way. Let's go to geometry real quick. Let's say at a rectangle right here, a green rectangle. It's a nice, 4 by 6 rectangle. And inside of this rectangle was another rectangle. I'm just going to put it like right here. This rectangle is a little smaller. Let's say that this rectangle is 1 by 3. And I asked you to find the area that I'm filling in now, this purple area. In other words, everything inside the green rectangle, but not including everything that's inside the red rectangle. So what would you do? Well, hopefully you recognize that you'd have to subtract. You would find the larger area, which is 24, 6 times 4. You would subtract the smaller area, the inside area, the hollow area, the empty area, and you would end up with 21. This volume problem that we're working on is going to be very similar. We have an outside shape, which is this blue shell. We're going to be subtracting an inside shape, which is this orange cylinder. Here's another view of it. So for now, let's treat this like two different problems. We're going to first find the volume of the blue shape, and then we're going to find the volume of the orange shape, and we're going to subtract. I don't have orange, so I'm going to use red here. Orange shape. So let's find the volume of these separately, and then we're going to subtract one from the other, and we will have our answer. The blue shape. The blue shape is made up of circles. Here's one of the circles. That's kind of the first circle right there. The most outside circle, the farthest circle, is this big guy. So every cross section of the blue shape is a circle. Circles have area. Areas are defined by radius. The radius of the circle is the distance from the axis of rotation, which is the line y equals -1, going right through the middle there. And this graph, here is y equals x squared. It continues off and continues. This is where it starts. This is y equals x squared. So the radius for any of the cross sections is going to be the distance from the axis of rotation and the graph. For some random circle in the middle, like this guy, there's another cross section. His radius is the distance from the axis of rotation and the graph y equals x squared. So let's go ahead and start setting up our integral already. The blue shape, I know I'm going to be accumulating circles. I'm going to be accumulating circles from x equals 1 to x equals 2. Those were the two vertical lines that bounded this shape. And I'm going to be finding or defining the areas of circles. So it's going to be pi multiplied by r squared. So right now, I'll just call it r squared. I'm going to do this in terms of x though. So I'm going to have to define that radius in terms of x. To get a sense of how we're going to define the radius in terms of x, let's take a look at the very first circle again. So there's the very first circle. Let's mark its radius in, how about purple. So there is the radius of the first outside circle. Okay, so I know that that radius is going to be 2. And the way I can compute that, I know this is at x equals 1, so this vertical line is x equals 1. The distance then from the red graph to the x-axis, the red graph being x squared, is 1. Here is the x-axis coming across here. This little part right here in red, from here to here, is 1, and that is from 1 squared. That is essentially f of 1. The distance from the x-axis to the graph is f of 1, which is 1 squared, which is 1. What I have to do is add another 1. Total radius for that first circle, 2. Let's take a look at the far outside circle then. What's the radius of this guy then? Same process. I know the distance, the radius, is from the axis of rotation, which cuts through the shape, to the outside of the circle. So here is the entire radius. Well, the entire radius is made up of two parts. This part right here, that's just going to be 1. And then this part, well, this part is the distance from the x-axis to the graph. That is the height of the graph, which would just be f of 2. This point right here is f of 2, which is 2 squared, which is equal to 4. The radius then, all the way up, including that little gap there, is actually 5. So for any radius, it's going to be pi times the radius squared. Well, the radius is just x squared. That gives you this part. X squared gives you the distance from the x-axis to the graph, plus 1. that takes care of the little gap between the x-axis and the axis of rotation. And since that defines my radius, I square that dx. So this integral represents the volume of the entire blue shape. Now, the volume of the orange cylinder in the middle is a little more straightforward. Let's erase all this other stuff. So the orange cylinder going through is made up of circular cross-sections, just like every other shape that we'll be dealing with these type of problems. But it has a constant radius all the way through. This graph, this orange shape, is not too complicated. The radius does not change. Each of these is just 1. Every radius is just 1. So we're going to integrate from 1 to 2 circles, and the area of a circle is pi r squared. So pi times 1 squared dx. Now, I'm not going to finish this problem right now, or maybe I will. I think I will. Let's finish the problem right now. So let's do the volume of the blue shape first. It is going to be, bring the pi out, from 1 to 2, x squared plus 1 squared. Well, I'm actually going to multiply that out. X squared times x squared is x to the 4th, and then we're going to have plus 2x squared plus 1 dx, and the antiderivative of this is x to the 5th over 5 plus 2x to the 3rd over 3 plus x. And we're going to do that from 1 to 2. This ends up being, get out of there, this ends up being 2 to the 5th over 5. Oh geez, so this is going to be pi multiplied by 2 to the 5th. 2, 4, 8, 16, 32. 32 fifths plus 2 times 2, 4, 8 thirds plus 2. The orange shape, the orange integral, is going to look like this. Bring the pi out. This is from 1 to 2 of just 1 squared dx. So just 1 dx. Antiderivative is going to be, the antiderivative of 1 is just x. We're going to do this from 1 to 2. So we get pi times 2 minus 1. And if you add up everything from the first shape and subtract the second shape, you end up with something roughly equal to, what's it say, 31.14 cubic units. Now, I would like to take one last look at this question. There it is. So there's my final answer. There we go, 31.14. So I'd like to take one last look at this same problem and apply what the book calls the washer method. Let me explain how this is going to work. Instead of treating this as two different shapes, accumulating areas of one circle, instead of accumulating areas of one circle and subtracting the areas of another circle, we're going to treat this as one shape called a washer. A washer looks like this. There are some washers. You know, I don't know who uses washers. Plumbers probably use washers. Somebody more handy than I am. But they have this donut shape. So what we can do is think of this volume not as a series of circles, but as a series of washers. The inside circle, the inside hole of the washer is going to stay the same shape, but the outside circle is going to get bigger and bigger and bigger. And if we can define the area of a cross-section, then we can do this integration just once using one shape, a washer, rather than finding the area of the outside shape or the volume of the outside shape and subtracting the area of the inside shape, or the volume of the inside shape. Area of one of these washers can be defined by the area of the large circle, which is pi r squared. I've used big R to represent the larger of the two radii, and pi big R squared minus pi little r squared. That gives me the area of a single washer. In this problem, big R is x squared plus 1, and R is equal to 1. This gives us the formula for the area of a washer. pi r squared minus pi r squared, or you can factor the pi out. And now we are accumulating washers instead of circles.